We're going to look at the mean value theorem, and this is an important theorem in calculus, and it gets used in a lot of other theorems, but it also has a really intuitive physical interpretation that makes a lot of sense. So this is kind of a neat theorem here. So basically here the conditions are the same as Rolle's theorem, and in fact Rolle's theorem is connected closely with this theorem. So it says if f of x is continuous on the closed interval ab and it's differentiable on the open interval ab, so those are the same conditions as Rolle's theorem. So if this is the case, then there's going to exist a c inside the interval ab such that the derivative of f at c is equal to the average rate of change of the function over the interval. Okay, that's what this is saying. So if I were to draw a picture here, it would look kind of like this. So let's say we have like a function here, and we'll say that this is a, and we'll say that this is b. And so the average rate of change over this function would look like that. So the slope here of this line is equal to this f of b minus f of a, b minus a. So it's just the change in the y values over the change in the x values. And that's the average rate of change of the function through those 2 points, the difference quotient. Okay, or you can think of it as the slope of the secant line. And so what this theorem is saying is that if this function is continuous on the closed interval and differentiable on the open interval, then there's going to be some c in here where the tangent line is parallel, and I don't know how well I found it here, but there's going to be some c where the tangent line of the function has the same slope as the secant line, or where the instantaneous rate of change of the function at that point is equal to the average rate of change of the function over the interval. Okay, so the slope of this line is equal to f prime of c. Okay, so basically then what you have here is that the derivative at c, so if the function is continuous on the closed interval ab, differentiable on the open interval, then there's going to be some point in that interval where the instantaneous rate of change is equal to the average rate of change of the function over the interval. Now I don't think I need to prove this here. You can look at the proof in your book, but as long as you keep Rolle's theorem in mind. Okay, so remember Rolle's theorem was just saying if you have a function that's continuous on the closed interval ab and differentiable on the open interval ab, okay, and if the function is equal at a and b, okay, so that you got this horizontal line, then there's going to be some point c inside this interval where you're going to have a horizontal tangent line, where the derivative is going to equal 0. So in a sense, the average rate of change from here to here, this secant line, right, is 0, and the Rolle's theorem says you're going to have some point in the interval that the derivative is equal to that average rate of change. So one way to think of this is if we turned this, or maybe if I, let me do it with Rolle's theorem here. So it's basically, the mean value theorem is a slanted version of Rolle's theorem, right? So if this thing were slanted, so you had your function, would be the secant line, and then this would be the line that's parallel to this secant line. Okay? And so this is kind of, or I can think of this is slanted if I changed it like this so that this was horizontal, right? So that these two were equal. This is a horizontal line, then there's going to be one point in here that you have a horizontal tangent. So in a sense, this is like Rolle's theorem just tilted on its side. Okay, and it could be tilted in different ways. It could be tilted this way or tilted that way or whatever. It's just a Rolle's theorem kind of rotated around. But it's basically Rolle's theorem, okay? And you use Rolle's theorem to prove this. It's just that you're shifting the situation, and there's a way to do that. And you can see the proof for that. It's basically creating a new function. That's the difference between the secant line and the function that you have, and that new function then fits the condition of Rolle's theorem, and then you can you set the derivatives of both sides, and then you have the new function's derivative is 0 because it meets the condition of Rolle's theorem, and then you can solve the remainder of the other. You take the derivative of the other side. You can solve for it ends up solving for this, and then you get the mean value theorem. Okay, so more importantly here is the homework problems. You're going to be asked to find the C value that satisfies the mean value theorem. So let's say I'm given the function f of x is equal to x cubed minus x squared, and I'm interested in it on the interval 0 to 2. Okay, and so first let's find the average rate of change on that interval. So it'd be f of 2 minus f of 0, right? 2 minus 0. So plugging 2 into here, I would get 2 cubed minus 2 squared. And then if I plug 0 in there, I'm just going to get 0. And then I would have 2 minus 0. Okay, and so this would be 8 minus 4 minus 0 over 2. So this would be 4 over 2, and this would just be 2. So the average rate of change of this function is 2. Okay, and so what this is saying is that there is going to be some point where the derivative is equal to 2. Some point in the interval 0 to 2 where the derivative is equal to 2. Okay, so let me graph this function. So we got x cubed minus x squared. And I'm going to, maybe I'll graph this on the interval 0 to 2. And maybe let me do like, I'll do negative 3 to 3, and then we'll do negative 5 to 5. I think that should do it. Ooh. Or let me just, I'm going to do a standard window here. Okay, so this is, it's a cubic here, and it looks like it does a little more than just flatten out here. So let's look at it in the interval from 0 to 2, okay? So what I'm going to do is I'm going to do this standard window. I'm going to go, maybe we'll do negative 2 to 2, and then I'll do negative 1 to 5, we'll say. And let me graph it. So yeah, so you're having it come down and go back up like this. Okay? Now, I can actually get the secant line pretty easy, because the secant line will be y equals mx plus b, right? Where m is equal to 2. That's our slope here. But notice that this goes through the point 0, 0, because you're wanting the line that passes through the point 0, 0, right? You're wanting the line that passes through the point 0, 0 and 2, 4, right? And you got the slope of 2, but then it also goes through the point 0, 0. And so what that means is the b is just 0. So you get y is equal to 2x. So this is actually the secant line. So let me actually graph the secant line. So I'll go down here to x. So here comes the secant line. So what this is saying is that there should be, since this function is continuous on the closed interval 0 to 2, and it's differentiable, because it's a polynomial, differentiable on the open interval 0 to 2, there should be some point in here where the graph, the tangent line is parallel to this line. And that makes sense. So let's see if we can actually find that point. Okay, so let's see if we can find it. So what I'm going to do is I'm going to take the derivative here and I'm going to set it equal to 2 to see if we can find the c value where it's equal to 2. So if I take the derivative of this, maybe I'll do it over here, f prime of x is equal to 3x squared minus 2x. So that's the derivative, and I want to set it equal to 2. I want to find when the derivative is equal to 2. And this is, not equal to 0, equal to 2. This is one of the problems in the assignment is going to want you to find the c value that shows you that this theorem is actually true. So now what I have here is a quadratic equation. So now you will have to solve some equations. So you'll have to think back to your algebra here and remember how to solve these. So for this one, I don't see how to factor this, so I'm going to use the quadratic formula. X is equal to the opposite of b, so the opposite of negative 2 plus or minus b squared, so negative 2 squared, minus 4, a is 3, c is negative 2, all over 2a, and again, a is 3. Okay, so this ends up being 4 plus or minus. This is 4, and this is going to be a positive 24. So this is like the square root of 28 all over 6. Okay, so now I can rewrite this 4 plus or minus 2 square root of 7. Okay, square root of 28 is square root of 4 times the square root of 7. So it would be 2 square root of 7 all over 6. And now I can simplify this, and I'm going to get, oh, and I'm not sure, this should have been just positive 2, not 4. And so this simplifies to 1/3 plus or minus, this will be the square root of 7 over 3. Okay, so hopefully at least one of these is going to lie in this interval. And if you actually figure these out, and I did this already, let me see if I can find my sheet here. So when you do the plus here, you actually get, oh, that's not it. Excuse me. Okay, so when you do the plus here, you actually get 1.21525 approximately. Okay, and this one actually does lie in the interval, so I think this is the point, right, where the slope is equal to, the slope of the tangent line is equal to the slope of the secant line. And so, but this one, when you use the minus, it's like negative 0.548584. Okay, so this is the c value then that satisfies the theorem. And so let's actually we can we'll plug it in and find out where it is and see if it's believable. So we'll put in the value. In fact, I can actually put in the actual value, 1/3 plus square root of 7 divided by 3. And then if I put that in, And that is believable there. That's where it's going to have a slope of 2. Now, if you want to check that, you could find the equation of the secant line. This one might be a little complicated because it's an ugly number. But you could do that and graph it and see if the two lines are parallel. There's also, if I hit second calc and I go down to this is a derivative function. And then if you look up above, it says normal, float, auto, real, radian, MP, calc, derivative at point. So it has some stuff up there, but I think that float point or whatever means it's not going to give you the exact. Can you see that up there? I'm not sure. It's kind of hard to read. It says finding the derivative at that point. And so it's not going to it'll give you an approximation. In other words, I'm going to type this in, so I'm going to do the 1 divided by 3 plus square root of 7, and then divide that by 3. And when I hit return, it's actually giving me the derivative. It's really hard to see on here. I don't know if I can zoom in. So it's actually giving me the derivative, and it gave it to me as like 2.0000001. Well, the derivative is actually 2, but the algorithm that it uses, it doesn't give you, it's giving you an approximation, and it's really, really, really close to 2, and it actually is 2 at that point. And so you found the right point there, even though it's not exact, okay? Because when it finds the derivative, it's not getting the exact value. It's getting a very, very close approximation. Okay, so there you go. That's the mean value theorem guarantees that there's a point where the function, the instantaneous rate of change of the function is equal to the average rate of change of the function over that point. Okay, what I want to do here is let me do one more of these. And what I want to do is I want to find, let's see, I have another one here where I want to find the point here on this interval, -1 to 2. Okay, now I want to ignore the conditions here because I want to show you that it's important that the conditions are met. Okay, and I just want to go ahead, take the derivative. I want to find the average rate of change, take the derivative, and see if I can get the C point. Okay, so the average rate of change would be f at 2 minus f of -1, 2 minus a -1. So f of 2 would be like 2 to the 4/5, okay, minus -1 to the 4/5, and so all over 2. This would be like 2 plus 1, right? So if I'm going to plug in this, so 2. So if I put in 2 to the 4/5, okay, it's going to give me, it's like approximately, so this is an approximate, like 1.7411, so on, okay, because this is a root here. And now if I do -1 to the 4/5, I get just 1. And then all this is divided by 3. So basically, I'm taking this number up here, and I'm subtracting 1. And then I'm dividing that by 3. And so this is an approximate here, but this is good enough. 0.247. Okay, so what I want to do is I want to find the place where this derivative is equal to this average rate of change of the function. So let me find the derivative first. So I'm going to bring down the 4/5, and then I get x, and then I have 4/5 minus 1. So I have 4/5 times x, and this would be 5/5, so this is -1/5. Okay, so what I want to do is I'm going to take 4, and maybe I'll put 4/5 x to the negative 1/5, and this is equal to 0.247. And so maybe what I'll do is I'll bring this over here. So I'll get x to the negative 1/5. And then I'll just, I'm going to type these things in. So I'm going to do 0.247 times 5/4. So I'm going to multiply by the reciprocal. And this whole thing is like approximately 0.30875. And now to get rid of this fractional exponent, I'm going to multiply both sides by the reciprocal, which would be a -5, okay? And then when I do that, raise that to a -5, look at what I get. So this, I get x by itself is approximately 356.4, okay? So this is what's going to give the derivative the same value as that, but notice this is not in this interval. It's not in -1 to 2. Okay, it's way outside that interval. Okay, and that's the only solution. So there is no value here that gives you a derivative of this. In fact, there is a value, but it's way outside that interval. So the value that would give you the instantaneous value that give you the average rate of change over this interval is way outside of that interval. So now let's graph this function and see if we can find a problem here. So I'm going to do x to the 4/5, and maybe we'll start with just a standard window. Oh, so sorry about this. Let me flip it around, and then we'll come. There we go. So here's the function. So this is a root function, and it's a odd power root, but it's also has the 4th power in there. So our function is actually would look something like this. It would be like f of x is equal to the 5th root of x, but that whole thing to the 4th power. And so the 5th root of x would be like something that would go down and around. It would look like a cubic on its side. Okay? But because we're taking it to the 4th power, instead of going down like this, it's going back up the other side. And you have this sharp point here. So in the interval -1 to 2, you have a point where it's not differentiable. Okay? It is not differentiable there. So this does not meet the conditions for the mean value theorem. It has to be differentiable. It is continuous over the closed interval, but it's not differentiable over the open interval. So when you take the average rate of change from -1 to 2, okay, and if you drew the line there, inside this interval, there's not any point that has the same slope as the average rate of change over the interval. And in fact, the average rate of change is way over there at 356. And so maybe what I'll do here is I will do a window from maybe -10 to 300 or we'll say 400. And this isn't going to necessarily give me, because this thing's going up higher. So what I need to do is maybe do a zoom. Oh, it's still going. And so I'm going to do a zoom fit to get a better picture of this. So there you go. So that zoom fit at this point, it can be kind of helpful. So I get this, this sharp point, and then it's going up, and then if I look at my window, I can see I'm going -10 to 400, so it doesn't change my x, but it does change the y so that you get the graph there. Okay, that's what it does to fit. It keeps your x's the same, but it changes the y's. And so now what I can do is I can put the derivative at at this point, this 356.4. So 356.4. And you can see what my derivative is there is 0.24700,313. So we're dealing with approximations, but you can see that I get to 3 decimal places, I get 0.247. So at this point, that's when the derivative is actually equal to this. Now in this case it looks steeper, but remember this is bigger than this. Okay, so this goes to 400, this goes to like 120. So so there you go. So this example is just showing you that you're not going to, if your function is not differentiable in this interval, you're not going to necessarily get a point in the interval that is equal to the average rate of change over that interval. So the conditions do need to be met.